Hi everyone, I'm Wang Cao from Wuhan University. Today, I'd like to share some of my work on GNSS and wheel inertial odometry integration for vehicle navigation, focusing on a few insights I found during the process. Before we get started, here is a question. What would you consider the greatest invention in our human history? Some might say the internet or computers, but from the perspective of someone studying vehicle navigation, I'd say the invention of the car is definitely one of the greatest. Since we live and move online, cars have greatly improved transportation efficiency and triggered countless innovations. In recent years, technologies like ADAS and V2X have become major topics in intelligent transportation. But have you ever thought about what all these rely on? I believe they all depend on the vehicle having some awareness of its surroundings. More precisely, knowing its position and orientation relative to certain landmarks. Only with this knowledge can it perform tasks like planning and control. To obtain this information, we usually rely on better sensor weights or more advanced processing algorithms. But both options often increase cost or computational burden. So, is there a simpler approach? Actually, we can use the vehicle's own motion constraints to improve its state estimation. That's the motivation behind my work, to explore a lightweight and general method for enhancing vehicle state estimation. Let's start with a basic kinematic model built on simple geometry and algebra. Assume a point mass P moving in 3D space. If we define its forward direction as the x-axis of the body frame, then in the global frame, this direction should be aligned with the velocity. This condition can be described using a cross product. It essentially means there's no set slip or vertical motion. In kinematics, this relationship is known as the non-holonomic constraint, or NHC. If we consider a rigid segment instead of a point mass, the NHC doesn't directly apply anymore since the segment consists of countless particles. But in real life, due to the friction, vehicles don't typically slide along the ground freely. Instead, we add wheels, like a bicycle. For the rear wheel of a bicycle, its motion is still limited to the forward direction, so the HC still holds. This leads to what we call the bicycle model, which is widely used in vehicle kinematics. Now let's think about a typical four-wheeled vehicle moving on the plane. Does the bicycle model still apply? In theory, yes. If we simplify along the vehicle's middle axis, it's still equivalent to a two-wheel model. According to the Ackermann geometry, the rear wheel's velocity should remain forward. But what really happens in practice? In the bottom right plot, you can see two sets of green points representing lateral velocity obtained from high-precision inertial navigation system. The maximum value reaches 0.4 meter per second. For a passenger car moving at around 20 meters per second, that's about 2%, not negligible. This means the assumption that velocity is parallel to the vehicle's forward axis doesn't hold anymore. So, what causes this phenomenon? A likely reason is that the instantaneous center of rotation deviates from the rear axis extension line, which creates an angle theta between the actual velocity and the middle axis. This could result from tire forces, road surface conditions, or sensor errors. But intuitively, it's due to planar maneuvers like turning or lane changes. So the question becomes, how can we reduce the effect of these maneuvers on the NHC? That's what motivated this study. In the following sections, I'll describe how I approached the problem from the perspective of robust state estimation. As mentioned earlier, the velocity of the equivalent rear wheel is no longer aligned with the forward direction. There is an angle theta between them. A straightforward idea is to rotate the forward direction vector by theta around the z-axis so that it aligns with the actual velocity. The equation on the right-hand side uses Roderick's rotation formula to describe this transformation. But as shown in the second line, calculating theta requires the lateral velocity component of the real wheel. So this correction method is essentially a form of mean shift. To apply it, we need polynomial regression or even machine learning, which goes against our original goal of developing a lightweight algorithm. A simpler alternative is to assume that the original constraint is still approximately valid, but we reduce our confidence in it. In filtering, this confidence is described using covariance. If the covariance inflates, the filter naturally reduces its reliance on the constraint. Some methods use adaptive filtering or machine learning to adjust the Q matrix. But in a sense, both are based on residual feedback. They're often hard to interpret and don't explicitly consider the vehicle's motion behavior. Now suppose the vehicle moves on a plane and the angle theta is small. Then the lateral velocity can be approximated. If we treat changes in theta and yaw angle as the same, we can relate it to angular velocity omega. But if we include a time interval in the model, it won't be general across devices due to the different sampling rates. If we assume the time step is small enough to use derivatives, after simplification and ignoring minor changes, we get a formula that's the product of a linear and angular velocity. Dimensionally, this is a centripetal acceleration. If we ignore the frame differences, this approximates the real-world centripetal acceleration in the Bascal model. Physically, centripetal acceleration reflects how sharply the vehicle is turning, so we can use it to quantify the driving behavior. We adopt the simplest strategy, assuming the Q matrix element sigma is linearly related to the magnitude of this acceleration. That completes the design of a variance inflation model. If we compare it with other approaches, it connects Q to behavior more intuitively than adaptive filtering, requires fewer and easier parameters than machine learning, and is more principled than using fixed empirical values. Now, let's look at how we validate this model. We conducted field experiments in Wuhan. T01 was inside Wuhan University's campus, a train-lined environment, and T02 was on the second ring road, an urban canyon scenario. The sensors and their key parameters are listed in the table on the right-hand side. The satellite observation results for both datasets are shown in the top left sequence plots. Based on our model, we also computed the centripetal acceleration magnitude shown in the last row of the figure in the bottom left. We compared our method with fixed noise strategies, one loose and one tight. Error curves in the north, east, and down directions are plotted. In period 1, 2, and 4, marked by dashed boxes, our adaptive method in purple achieved the lowest error. All the three intervals have significant positioning errors, so we focus on them. Period number 1 occurred in a train line area. Period number 2 near a sideways overpass. And period number 4 on a forward-facing overpass where the vehicle was partially blocked and changing lanes. Despite the challenging conditions, our method still performed the best. Now let's have a look at the third scenario. Here, the vehicle entered a tunnel, a complete GNSS outage. Even in this case, our method had the smallest RMS and max errors. The table on the right-hand side lists the statistics for both the scenes. Our method gave the best performance in the north and east directions, but didn't perform in the down direction for T02. That's expected, since our model is entirely based on planar motion and doesn't improve vertical accuracy. To further test its performance, we selected several turning-rich road segments as shown on the top left. We ran simulated GNSS outages and compared our method with a machine learning approach proposed by Xu et al. As in earlier tests show, our method has the best performance among all non-machine learning approaches. That is, the purple curve usually shows the smallest error, even during long-term outages shown in the bottom right. Our method was on par with the machine learning method. Statistically, our method achieved the best average RMS and the second best max error overall. Now I'll give a short summary and share some future directions. To address the failure of the NHC and the complex planar motion, we proposed a method to quantify driving behavior based on the Basel model. The derived quantity approximates real-world centripetal acceleration, and we linked its magnitude linearly to the covariance. Results showed that the proposed method can improve planar positioning accuracy. Looking ahead, we have a few open questions. Can we combine mean shift and variance inflation for even more robust estimation? Can we better model the tendency of the vehicle to leave the plane? And if the flight plane becomes a more complex manifold, how can we generalize this approach? Here are the references cited in this presentation. Thank you very much for listening. If you have any questions, please feel free to contact me by email.